Hello, welcome to Amekadam's channel, and in this lecture we will see Butterworth band stop filter, or you can say band reject filter design. So specifications are as follows. They have mentioned the order of the filter, n is equal to 4. The center frequency is also mentioned 1.4 GHz, bandwidth 12%, and impedance R0 is 55 ohm. Just I will add another thing over here. Let's say if they ask calculate upper and lower cutoff frequency. So we'll see the designing and also the calculation of upper and lower cutoff frequency. So I will mention the given data over here one by one. So I have to design band stop filter, or you can say band reject filter. For Butterworth response, or you can say maximally flat response, it indicates that there is no ripple in the pass band. Now n is equal to 4, f naught is given as 1.4 GHz and delta as 12%, so delta is 0.12. Now we'll calculate, this is fractional bandwidth. Delta is nothing but fractional bandwidth. So we'll calculate actual bandwidth as f naught into delta. So that is 1.4 GHz into 0.12. So that turns out to be 0.168 gigahertz. So I can calculate f u, that is upper cutoff frequency, as f naught plus bandwidth by 2, and fl as f naught minus bandwidth by 2. So this is 1.4 plus 0.168 by 2, and here it is 1.4 minus 0.168 by 2. So my upper cutoff frequency is 1.484 gigahertz, and the lower cutoff frequency will be 1.316 gigahertz. So I have calculated the upper and lower cutoff frequency. Now I have to design the actual filter. So first of all, we will design the low pass filter prototype. So for that we require the coefficient. So GK is calculated as 2 sine 2k minus 1 pi by 2n, where k is running from 1 to n. So here the order is 4. So k will have value as 1, 2, 3 and 4. So I will have G1, G2, G3 and G4. So let us calculate this one by one. I will type this equation of calculator. So 2 into sine, instead of k I will use variable as a minus 1 into pi as 180 divided by 2 into n is equal to 4. So calculate for k is equal to 1, that means a is equal to 1. So it turns out to be 0.7654. So again G4 will be again 0.7654, and calculate for 2. So it turns out to be 1.8478. Again for G3, you can verify these results for G3 and G4 also. So we'll proceed for the designing of band stop filter. So we'll have solution 1. Here first of all I will design the low pass filter prototype. N is equal to 4. So the first element I will consider as inductor in the series arm. then capacitor, inductor and capacitor. So these are the four elements, and these elements are denoted as L1, C2, L3 and C4. Rather, instead of this one, I will consider this as G1, G2, G3 and G4. Now I will transform this into band stop filter, you can say band reject filter. Now the transformation is done like this. For the series inductor can be transformed into parallel combination of inductor and capacitor. The shunt capacitor or the capacitor is transformed as series combination of capacitor and inductor. So again here I will have parallel combination, and here I will have series combination. So this I will have L1, C1, L2, C2, L3, C3, L4 and C4. This one is the low pass filter prototype designed for the normalized frequency as 1 radian per second and normalized impedance of 1 ohm. Now we have to calculate these components values for band stop filter. So I have to calculate L1, C1, L2, C2, L3, C3 and L4, C4. So here the first element is inductor. Again L1 inductor, so G1 will be the numerator. For capacitor, the nature of the element has been changed, so it will be 1 by G1. Here it is capacitor, so here it will be 1 by G2. Here capacitor and again here capacitor, so G2 will be in the numerator. G3 inductor, so here G3 will be in the numerator. Inductor, but here it is capacitor. This one is capacitor. So nature of the element has been changed, so 1 by G3. Here it is capacitor, C4 capacitor, so it will be G4 in the numerator and it will be 1 by G4 in the denominator, or G4 in the denominator. After this we have to apply the impedance scaling. Impedance scaling is applied as multiplication by R0 for, or Z0 you can say, for inductor, and division by R0 for the capacitor. Now frequency scaling, division by omega naught for each and every element. And now this delta in the design we have considered as 0.12. So this delta for the design of band stop filter is placed along with G. So here I will have delta over here, so we'll calculate these components by substituting values of the G, R0, delta and omega naught. So I will show the calculation only for the first element, and remaining calculation you can easily do. So L1 G1 is 0.7654 into R0 55 into delta 0.12 divided by omega naught, so 2 into pi into f naught, and f naught is mentioned as 1.4 gigahertz, so 1.4 into 10 to the power 9. So if you calculate, this turns out to be 574 picohenry. Yeah. So again, yeah, you will have L1 is equal to 574 picohenry. C1 turns out to be 22.5 picofarad. L2 28.2 nanohenry. C2 0.46 picofarad. L3 1.391 nanohenry, C3 9.322 picofarad, L4 68.08 nanohenry, and C4 190.5 femtofarad, or one can write it this as 0.1905 picofarad. While writing femtofarad, F should be small and this F should be capital. So I will complete the design by placing RL and RS over here, which is equal to 55 ohm, and Vs over here. So this is about solution 1. Solution 2 is quite simple, as the order is even order is an even number. So solution 2 we can easily draw by keeping this as a reference thing. So we will have solution 2 directly. So that when we will design, actually this solution will come from the low pass filter prototype, where the first element will be considered as parallel capacitor, and then inductor, capacitor and inductor. 4 elements you have to consider. This will be G1, G2, G3 and G4. And now this capacitor will become, when you are designing band stop filter or band reject filter, this will become series combination of capacitor and inductor. This will become parallel combination of inductor and capacitor. This capacitor will become series combination, and this inductor will become parallel combination of inductor and capacitor. So I will have L1, C1, L2, C2, L3, C3, L4 and C4. Now these values we can easily write down by observing solution 1. So if you see this one, if you flip this thing, then you will have this network. If you flip this network, so L1 and C1 is nothing but L1, L4 and C4 over here. C2 and L2 will be C3 and L3 over here. L3 and C3 in this design solution 1 will be L2 and C2, and C4 and L4 will become L1 and C1 over here. So I will directly note down the values. C1 will be 0.1905 picofarad. L1 will become 68.08 nanohenry. Then L2 will be similar to L3 in this case. So L2 I will write, L2 will be 1.391 nanohenry. C2 will be 9.322 picofarad. C3 will be 0.46 picofarad. L3 will be 28.2 nanohenry. And then I will have L4 as 574 picohenry and C4 as 22.5 picofarad. So this is solution 2. We complete this thing by placing RS and RL over here, 55 ohm, and I will have VS over here. So when the order of the filter is an even number, we can easily determine solution 2 from solution 1. That's all about the Butterworth band stop filter. We have seen the numericals for low pass, Butterworth low pass, high pass, band stop and band pass filter. We have seen 2 numericals each. So in the next lecture we'll design the Chebyshev filter, Chebyshev low pass filter, then high pass, band stop and band reject filter. Basically the for the Chebyshev filter, the procedure will remain same, exactly same as that of Butterworth. Only the coefficients G1, G2, these will go on changing, because in Butterworth there is no ripple in the passband, and in Chebyshev there is a ripple in the passband. So only the coefficient of G will change, the coefficient G will change, otherwise the design procedure will remain same. We can directly design the low pass filter, but for band pass and band stop filter, one has to design first of all low pass filter prototype, and then one has to transform into band stop filter accordingly. So that is all about the Butterworth filters. Thank you.